as energy. What would be a convenient way to measure the energy content of matter? Well, the chemist's answer is to measure the energy using a thermometer. We define the temperature to be the average kinetic energy of the particles in the matter. The more motion that the particles exhibits, the greater the temperature. The fundamental relationship in making a temperature measurement using a thermometer relies on the state of the matter that makes the thermometer and its energy and density. There's an inverse relationship between the energy of the matter and the density of the material making up the thermometer. So, as the kinetic energy and temperature of a substance increases, the density of the material decreases. Result, if the mass is constant, as the temperature increases, the volume of the thermometer material also increases. Fine, but how is the thermometer actually measuring the temperature of bulk matter? Let's say we place the thermometer in the middle of some hot matter at a temperature greater than the original thermometer. It's also critical that the thermometer is much, much smaller than the amount of matter we are measuring. The matter's particles have considerable kinetic energy, and they collide with the thermometer's walls, transmitting that energy to the particles within the thermometer. These particles now start moving around more than they did. Thus, their kinetic energy goes up. With this increased energy of the particles of the matter in the thermometer, the density decreases because the particles are moving all about, taking up more volume. The result that we see is the material in the thermometer travels up the tube. This will continue until the average kinetic energy of the particles in the thermometer are equal to that of the particles of the matter in the substance we are measuring, and the material then will stop climbing up the tube. Because the matter has many more particles than the thermometer, we can ignore any energy transfer that might occur from the thermometer to the matter. That much energy we will consider to be too small to be significant. The magical fluid mercury was found to be a wonderful chemical for use in measuring temperature. The German physicist Daniel Gabriel Fahrenheit evacuated the air from a tube, which he then melded onto a reservoir bulb filled with mercury. He assumed that temperature was directly or linearly related to the volume of mercury, and the height of the mercury in the tube would be directly related to the total volume of the mercury in the thermometer. Because of the assumed linear relationship of the temperature to the height of the liquid in the thermometer, Fahrenheit knew that all he needed was 2 points or controls to establish a line and define the calibration of the thermometer. So he chose 2 controlled values that he could easily create in the lab in calibrating his thermometer. He measured the 2 controls, marking both of these temperature measurements with lines on his thermometer tube, established values for these 2 set points, and then put equally spaced lines and values between the set points to establish a numerical temperature scale. The 2 set points that Fahrenheit used to set up his scale are now clouded in the mists of time, but the prevalent idea is that his low energy value was the melting point of ice, which he set at 32, and the second was the body temperature of a healthy man, which he set at 96, which we now know is 2.6 degrees low because of our modern recalibration of his thermometer. He liked, though, this 64-degree interval, because all he needed to do to finish his scale was to mark degree lines bisecting the 64-degree range into 6 equally spaced intervals. The equivalent math is 2 to the power of 6 equals 64. If we extrapolate and continue marking the thermometer with evenly spaced lines above the 96 value, we eventually get to the temperature of the boiling point of water at 1 atmosphere, the value of 212 degrees Fahrenheit. Notice how we denote degrees with the 0 superscript before the F. This is to let us know that this is not an absolute temperature scale. We'll discuss this absolute concept in just a few minutes. A few years later, the Swedish astronomer Anders Celsius built a thermometer like Fahrenheit's using the same thermometer material, mercury, but he chose two different set points. He used the freezing point of water as one set point and gave it the value of 100, and the boiling point of water his second set point, which he set at 0. Now, this looks a bit weird and inverted to us now, but we must remember that Celsius was an astronomer whose best work was on cold winter's nights in an observatory up on the hill in the snow. He was interested in how cold it was outside, not how warm. It wasn't until later that the Swedish botanist Carlos Linnaeus inverted the scale, making 0 degrees Celsius the freezing point of water and 100 degrees Celsius the boiling point of water. This 100-degree base 10 scale worked well with the base 10 metric system and eventually became one of the more prevalent temperature scales. But there's a fundamental problem with our measurement of temperature that makes it unacceptable when compared with all of our other physical measurements that we've been using up to this point. What does it mean when matter has a length of 0 meters, or a mass of 0 grams, or a pressure of 0 bar? Well, the answer is obvious. When these values are 0, there's typically 0 matter. We call these measurements absolute measurements. The 0 means there is nothing there to measure. Now, if we measure energy using the Fahrenheit or Celsius thermometers, we see that 0 degrees Celsius or 0 degrees Fahrenheit does not mean 0 energy content in the matter. Yes, we say the matter is cold, but the particles are still moving. These temperature scales are not absolute and have limitations in measuring energy directly. A scientist who realized this limitation was Sir William Thomson, who was more famous in his day for laying down the first transatlantic telegraph cable from England to the Americas. He was later knighted by Queen Victoria and became known as Lord Kelvin. Kelvin developed what was called an air thermometer. A facsimile of this device is to imagine just a small bit of air trapped in a big metal sphere fixed with a pressure gauge and a Celsius thermometer. What was done was to put the sphere in contact with several substances of varying temperatures and read the pressure and temperature of the air in the sphere. We then plot the pressure versus the temperature. We can take and refill the sphere with a different amount or even a different kind of gas, or change the size of the sphere and redo the measurements. Again, if the amount of gas is kept low, we see that each of the sets of data give a linear relationship, and if we extrapolate each of the lines to 0 pressure, you obtain the same value for the temperature, minus 273.15 degrees Celsius. Kelvin surmised that this was the temperature in which matter has no energy. So he set this value to be absolute 0, or 0K, after our dear Lord Kelvin. Notice there is no degree symbol associated with this temperature scale because this is an absolute measurement synonymous with the meter, kilogram, and others. Now Kelvin has established his first set point, absolute 0. So all he needs to complete his temperature scale is a second set point. He could have chosen anything with any number scale he desired, but most folks had Celsius thermometers, and it made sense to choose a value that would not make these instruments obsolete. So he set up a relationship that would make these thermometers useful in measuring absolute temperatures. His second set point was the freezing point of water, which he assigned the value 273.15 Kelvin. A convenient result of his choice for the second set point is that a 1 Kelvin change in the absolute scale is identical to a 1 degree change in the Celsius scale, making it easy to convert between the two scales. All we need to do is take the measurement in Celsius and simply add 273.15 to convert it to a temperature in the absolute temperature scale in kelvins. The simple equation that represents this conversion between the Celsius and Kelvin temperature scale is temperature in Kelvin equals temperature in Celsius plus 273.15. You can see on this slide a side-by-side comparison of the Fahrenheit, Celsius, and Kelvin scales, with common set point temperatures on each thermometer. Since all these thermometers are measuring the same bodies at the same temperatures, and since they all are linear scales, there has to be a simple linear relationship between all of them. We already know the linear relationship between Celsius and Kelvin, with the relationship being temperature in Kelvin equals temperature in degrees Celsius plus 273.15. The linear relationship between the Celsius and Fahrenheit scales turns out to be the temperature in degrees Fahrenheit equals 1.8 times the temperature in degrees Celsius plus 32. So what is the value in all three scales of a typical room temperature measurement of 77.0 degrees Fahrenheit? Well, using algebra to rearrange the equation and then entering in the values into the resultant equations, we obtain an equivalent temperature of 25.0 degrees C in the Celsius scale and an absolute temperature of 298.2 K in the Kelvin scale. Now, for our purposes, we will treat the values in these conversion equations, the 1.8, 32, and 273.15, as exact values. By doing this, we will force our original given value to be the value that determines the precision and dictates the number of sig figs for each computation. Now, in our last example, the number of sig figs for the Celsius conversion was 3, and that of the Kelvin conversion was 4. We also used textbook rounding rules of 5s to complete that Kelvin computation, if you notice. Wonderful. We now have a variety of ways of measuring properties of bulk matter: mass, length, moles, volume, density, pressure, and finally, temperature. Using these state measurements, we ultimately hope to completely quantify the state of any system and thus have the ability to reproduce that system anywhere and at any time we want. Pretty powerful stuff. Well, catch you soon.